Namaste students, welcome back to Rama Teaches You. Today we are going to do chemical bonding and molecular structure, the English video part number 3. So in this video, we are going to start with a brand new topic called the valence shell electron pair repulsion theory. Okay, so the valence shell electron pair repulsion theory is basically how you actually start viewing the three-dimensional structure. You are no longer bounded by the two-dimensional structure of Lewis. Okay, now we are going to start the class. Let's hope you understand this class really well. Let's start. Okay, so we have the resonance and Vesper theory. First and foremost, we have to understand what resonance is. Okay, now what is resonance? You must have heard a lot about resonance when we were talking about structure of atom. Like there is some resonance that is shared inside a molecule that allows it to become stable. You will learn more about this when you go to organic chemistry, because in organic chemistry, for some reason, your the whole resonance is quite prevalent. Okay, so let's start. The phenomenon of resonance was put forward by Heisenberg, the same person who discovered the uncertainty principle. According to this concept, whenever a single Lewis structure cannot describe all the properties of a molecule, a number of structures with similar energies, position of nuclei, bonding and non-bonding pair of electrons are written to describe all the properties. Okay, so what is happening here? Heisenberg is trying to tell us that there is not a single, like there are some molecules in which a single structure does not exist. That is, it can stay as various different types of structures, and all of them have the same positioning of atoms, the same number of valence electrons, the same number of bond pair electrons. Everything is the same. Only the thing is, they are not existing as one structure. Imagine that you are sitting in front of me, right? You are sitting in front of me and we are viewing the camera. Imagine that there is another Drupad right next to you who has the same features as you. He is also having the same energy level. That is, he's also basically trying to learn what you are trying to say, but you both have different internal bonding structures. That's it. Every positioning is the same. Your head is where it should be, your heart is where it should be, your hands, legs, torso, everything is where it should be. But the arrangement of bonds, the arrangement is slightly different, which makes both of you, exist at the same time. Now, you should not be surprised when such a kind of situation happens, because we have already discussed that electrons can act as a wave as well as a particle. They are able to do both the things in one single go. Am I right? So similarly, you can have structures with different properties, having the same shape, having the same configuration of atoms together, and that property is known as resonance. The actual structure is between all the three combined structures and is known as a resonance hybrid. Now, if I want to describe you, you know how I would describe you? As a hybrid structure of you and your clone. Similarly, in the case of resonance, we have the final structure described as a hybrid of all these different structures having the same energy level. Okay, so and the different individual structures are termed as the resonating structures or canonical form. Okay, I'll give you a small example of what I'm talking about. See, we have already discussed that there is something known as a benzene, right? Have you ever heard of the molecule benzene, Dhulpad? Benzene ring? Have you ever heard of a benzene ring? Benzene ring. Yeah. Have you ever heard of it? Yeah. No, right? So basically, what does a benzene ring look like? Okay, a benzene ring look like this. Okay, you have a double bond here, a double bond here, and a double bond here. Now, see, basically, the molecular formula of benzene is C6H6. That means every single corner of this benzene has a carbon, and every single carbon is attached to a hydrogen. Okay, so basically, if we consider, if we start numbering them as we did in carbonized compounds, this will be number 1, number 2, number 3, number 4, number 5, and number 6. Right? So this is the basic, this is one of the resonating structures of benzene. Now you can see that there is a double bond between carbon 1 and carbon 6. There is a double bond between carbon 5 and carbon 4. There is a double bond between carbon 2 and carbon 3, right? But there is another structure that equally at the same time exists in a benzene. That is this one. Here, here, and here. Again a hydrogen, one more, one more, one more, and one more. Okay, now this is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. Now there exists a double bond between carbon 1 and carbon 2, carbon 3 and carbon 4, carbon 5 and carbon 6. So both these structures of benzene exist at the same time. They exist at the same exact time. Now, since we cannot, once we write something in a piece of paper, we cannot change it, right? So how can I represent both these benzene rings at the same time? Because both of them exist at one any particular point of time. Both these structures exist. Okay, so how am I supposed to represent something like this in a two-dimensional textbook where the pages once printed cannot be changed? I do this with this. This is what a benzene ring looks like. Pardon my handwriting, my drawing. I'm not that capable. So basically, you have a structure something like this. So this is known as a resonance hybrid. These two are known as resonating resonating structures. Okay, now what did you understand something like this? Did you understand what I'm trying to tell you, Drupad? Is it becoming a little bit clear, or should I explain it a little bit more? We are going to go deep into why this is happening. You understood, right? Very good. Next. So this phenomenon is called resonance. Okay, the shifting of bonds from one between two atoms to another two atoms is what we call resonance. The double-headed arrow are used in between the canonical structures to separate them as shown in figure. So basically, I can write an arrow like this. It's a double-headed arrow. You know what this means? These two structures of benzene do exist at the same time. They can become anything they want. So you cannot say that this is the structure of benzene. No, this is the structure of benzene. This one. Okay. This whole thing becomes the hybrid structure of benzene. Next, we are going to understand what happens in ozone. Okay, let's understand this. Experimentally determine oxygen bond length in the O3 molecule are the same. That is 128 picometers, which is not represented by either structures A and B. Look at this. See, we know that the bond length is directly proportional to the number of bonds that, sorry, it is inversely proportional to the number of bonds that are between two atoms. For example, the single bonded carbon. Okay, when two carbons form a single bond, its length is greater than when it forms a double bond between these two carbons, and it is still greater than the number of triple bonds. If a carbon-carbon has triple bond, then the bond length actually reduces. But when we study the structure of ozone, we learn something crazy, that even though even though one is a double bond and one is a triple bond, ideally speaking, they should have two different bond lengths, right? They should have two different bond lengths. That is 121 picometers and 148 picometers. But when they did this X-ray experiment and when they used the spectroscopy and all of that stuff, they were able to realize that both these bonds were of the same length. And that is where Lewis diagram fails. Both of these are examples of Lewis structures. But when you actually do the experiment and figure out the distance, you realize that both the bonds are not of the same length. Both the bonds are of the same length. They are not separated. Okay, and what is the reason behind it? Thus, the oxygen-oxygen bond in O3 molecule is an intermediate between a double bond and a single bond, and it is represented by a resonance hybrid structure C. So, you can say that not one single bond exists, not one double bond exists. There exists a single bond between single bond between these two these two oxygen atoms, okay, with the third oxygen atom, and there exists a partial bonding between these two oxygen atoms and these two oxygen atoms. It's called basically a partial bonding structure. Now, this is also called a resonance hybrid. Okay, now neither of them have a double bond, but in other words, they both have a double bond. See, this is where our brain starts to open up. You are saying that there is not a single double bond, but there is actually a partial bond next to the single bond. And if you look at it closely, why am I saying this? I'm saying this because if we look at the structure, the double bond should have a length of 121 picometers, but the final bonding structure is somewhere in between. It is not 121, it is not 148, it is 128 picometers. So there is a structural change that is happening here. Neither this nor that, neither double bond nor single bond. It is a combo. So I can with 100% guarantee say that a single bond also does not exist, a double bond also does not exist. Somewhere in between is what the oxygen-oxygen bond length is. Are you able to understand this? Are you able to follow me? Okay, let's move on. Rules for writing the resonance structures. Only those canonical or contributing structures contribute towards resonance which obey the following rules. Number one, in all the contributing structures, position of atoms should be the same. What their meaning is, see, when I was drawing the structures of benzene, these two structures of benzene when I was drawing, did I change the position of carbon? No, right? I did not change the position of carbon. Every single carbon is having the same position in both the benzene rings. The position of hydrogen is also not changed. If you physically change the places of carbon, then you are not having a resonating structure. You are having a different molecule altogether. Right? That is rule number one. They should differ only in the position of electrons. That is, the places where the single bonds and the double bonds exist can interchange their positions, but not the physical atoms. If the physical atoms change, you have a new molecule altogether. I hope you understand this, Drupad. Number of unpaired electrons must also be the same. The number of unpaired electrons must also be the same in all the contributing structures. Now let us look at here. How many unpaired electrons are present in every atom of carbon in the benzene ring? There is 0 valence electrons. Am I right? Because all the 4 electrons are being used here, used here, used here, used here, used here, and used here. So the number of valence electrons here is 0. The number of valence electrons here is also 0. So basically you are having 0 valence electrons. Let us take the example of oxygen. Now, how many valence electrons are present here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 valence electrons present here. How many valence electrons are present here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 electrons present here also. Okay, next. So both these are resonating structures. All they have done is exchanged their electrons. That's it. That's all they have done. Okay, so by exchanging their electrons, they are maintaining the number of valence electrons to be the same in both of them. Okay, that's the rule that you need to follow. The energy of the contributing structures should be nearly the same. What do they mean by this? Energy should nearly be the same. See, what are the different types of energies that exist in a molecule? You can have the attractive electron and proton energy, attractive potential energy, that's what we call it. Then you have the repulsion between the electrons, that is the repulsive potential energy. You have the kinetic energy of the molecules, the rotational energy, the vibrational energy. All of these energy levels together give us the overall energy of the molecule. Okay, it gives us the overall energy of the molecule. Now, what I am boldly saying is both these energies, all these energies, when they total, the total energy of this ozone molecule and this ozone molecule is the same. Understood? It is exactly the same or almost similar. Okay, same or similar. Next, stability of a resonance hybrid. Now, in order to find the most stable hybrid form, follow the following rules. Number one, non-polar molecules are always more stable as compared to polar molecules. Now, what is a non-polar molecule? A non-polar molecule is where polarity does not exist. For example, a hydrogen-hydrogen bond, a oxygen-oxygen double bond, a nitrogen-nitrogen triple bond, a chlorine-chlorine single bond. Okay, here because the electronegativities of both the atoms that are forming the bond is exactly the same, we can say that the shared pair of electrons will always lie in the middle. Okay, the shared pair of electrons will always lie in the middle. Okay, due to which what will happen? Neither of them will have polarity, neither of them. So if you want to have a stable structure, you have to eliminate polarity. Okay, now do all molecules that are hybrids not have polarity? No, but we can always choose a molecule in which the polarity or the repulsive forces that exist or the attractive forces that exist are the least. That's it. That's all we are talking about. It's not saying that we should basically remove polarity. It's just giving us a small suggestion that a non-polar molecule would exist in nature with much more stability as compared to that of a polar molecule. Next, the canonical forms having more number of covalent bonds is more stable. The more covalent bonds you have, covalent bonds means shared bonds, that is double bonds and triple bonds. If you have more number of bonds that are between the atoms, you are more stable. Why are you more stable? Because you are not basically holding on to electrons all to yourself. You are sharing them between bonds. See, if you think about this, Drupad, if you are falling off a cliff and I am basically trying to hold you, if you're like falling off a cliff and I'm holding you by one hand, would you feel safer? Or if I hold you with both hands, the both hands one will be more safer, right? You will be more stable. At least I would have a better grip on you. Similarly, the more number of chemical bonds that you have, it is better to have more chemical bonds. Okay, more chemical bonds, more bonds equals more stability. Oh shit. So canonical forms having more negative charge on electronegative atoms and positive charge on electropositive atoms or less electronegative atoms is more stable. So what are the things? More having negative charge on electronegative atoms and positive charge on electropositive atoms. You know what that means, Drupat? For example, this is what they're talking about. You have HCl. Now, can you please tell me which is the more electronegative atom? Which is the more electronegative atom, Drupat? Fluorine. And the electropositive atom is hydrogen. Now, what is happening here? The shared pair of electrons is moving towards fluorine, right? So basically, it has a slight negative charge and this has a slight positive charge. Now, This is a partial charge. This is not the charge that they are talking about, but I'm just trying to give you an idea what that means. Okay, a positive charge on an electropositive atom and a negative charge on an electronegative atom, you will realize more about this. Okay, like for example, if you have there, what is happening is the complete electron is getting transferred. You have an actual positive charge and a negative charge. Okay, this is just an example that I'm trying to provide you. Now let's move on. What is the resonance energy? The difference the difference sorry the difference in the energy of the resonance hybrids and the most stable contributing structure having the least energy is called the resonance energy. For example, benzene has a resonance energy of 150 kilojoules per mole or 36 kilocalories per mole. Okay, so what is one calories? How many joules? Do you remember it from chapter number 1? 1 calorie is how many joules? 4.18 joules. Remember that. Okay, 4.18 joules, 1 calorie. Okay, next, classifications of some misconceptions associated with resonance. So people who don't understand resonance exactly or completely, they are always going to be at a disadvantage when it comes to organic chemistry, because in organic chemistry you have to deal with so many reactions. Okay, when you deal with so many reactions, you have to know how to position your electrons during the reaction. Otherwise, you will have to be a rattu. A rattu is a Hindi word which means basically rote learning. You will have to mug up everything. Okay. Some people understand, like for example, when I draw a structure, I don't actually remember what is happening in the structure. I just go with my gut and most of the reactions. There are some reactions that you will have to mug up. There are a few reactions, but majority of the reactions, if you know what is happening, you can actually do the whole reaction by moving the electrons. Okay, the movement of electrons, if you understand it thoroughly, organic chemistry will be a breeze for you. Okay, let's move on. Several misconceptions are associated with resonance, and there is a need to dispel them. One should remember that the canonical form are only imagined structures, they do not exist in real life. So, what they're trying to tell you is these two structures, the A and the B, do not exist in real life. See, both of them cannot exist at one time, right? You cannot be a lefty and a righty at a single time. Okay, so what they're trying to tell you is this is a structure that actually exists in nature. Canonical form is just a way for us humble students to understand the vast unknown of what chemistry is all about. This is going to be a recurring theme of chemistry. Okay, for us to understand something, we have to basically dumb it down. It may not be exactly what is happening in front of you, but you have to dumb it down so that your brain can process it. So that's why we created the canonical form. It is just an imaginary structure, it does not exist. The molecules do not exist for a certain fraction of time in one canonical form and for another fraction of time in another canonical form. That is what they're trying to tell you. It's not like they're not sharing this responsibility. They're not saying, okay, you hold on to the single bond, I will have the double bond. Now, I will have the single bond, you hold on to the double bond. That is not what is happening here. So basically, you are having a hybrid structure every single time. But to understand how the hybrid structure actually came, you have to understand the canonical forms. So it is not useless information. Now, unlike tautomeric formulas, ketones and enol forms, the canonical form are not in the state of equilibrium. Okay, so equilibrium means what? Equilibrium is a state in which the overall energy is the minimum. Okay, like for example, you have a ramp like this. Okay, imagine that you have a ramp like this, a ramp that going like this. Now you have a ball placed here. The ball will basically roll down and come here, and it will roll down and come here, it will roll down and come here. Finally, it will settle at the center. We call it the equilibrium position of the ball. Understood? We call it the equilibrium position of the ball because that in that particular position, the ball is having the least amount of energy. Okay, it does not have a very high kinetic energy because it is stationary. It does not have a very high potential energy because it is at a lower energy level. Okay, the molecule as such has a single structure which is the resonance hybrid of the canonical form and cannot be depicted by a single Lewis structure. So most of the hybrid structures that we have cannot be described by Lewis structures. Lewis diagram fails in doing so. Okay, now let us look at one question here. All the chlorine oxygen bonds distance in the CCl4 minus is 144 picometers. What explanation can you give for this? So, how first and foremost, we will understand how many structures or how many canonical structures are present. Okay, now what does an usual carbon this is basically chlorate. This is a chlorate molecule. Okay, what is the chlorine, not a molecule, an ion, chlorate ion. In a chlorate ion, what happens? Chlorine has how many electrons? It has 7 electrons to share. So what's it doing? It is sharing 2 electrons with this one, 2 electrons with this one, 2 electrons with this one. It is left with how much? It is left with one extra you can say one extra chlorine, right? Like 7. Yes. So what it is doing is basically it is having a coordinate bond here. Okay, a double bond, double bond, double bond, and it is having a coordinate bond here. Now this oxygen atom got an electron from somewhere else. It one electron from chlorine because chlorine only had how many electrons to share? It only had 7 electrons to share. It has shared all the 7 electrons, 6 electrons with these 3 oxygen and is sharing 1 electron with this oxygen, and this oxygen took 1 electron from somewhere else. That is why there is an overall negative charge in ClO4 minus, because oxygen did not bring its did not actually have all its it actually took one extra electron from somewhere else. Okay, it took 1 electron from chlorine, 1 electron from somewhere else. Therefore the whole molecule has 1 extra electron. Therefore you have a ClO4 minus negative charge. Now this can be changed via having double bonds here, 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 and a single bond here. You can also have basically a double bond here, a double bond here, a double bond here, and a single bond here. Or you can have a double bond here, a double bond here, a double bond here, and a single bond here. Okay, so basically what is happening here is, because there are 4 double bonds, there are 3 double bonds and a single bond, that single bond is being passed on. It is being passed on by the 4 oxygen atoms. Thus, it has 4 canonical structures, but it has only one hybrid structure, that is basically a single bond here, a single bond here, a single bond here, a single bond here, and a partial double bond here, a partial double bond here, and a partial double bond here. That is the reason why the ClO4 minus has all the bonds of equal length, because they do not exist as 4 different structures, but they exist as one single hybrid structure, that is this one. Understood, Drupad? Is this absolutely clear to you? Is it hard? It's fine, right? Okay, I will try to make this class with I usually, when I teach chemistry, I'll try to give as many real world counterparts of theories that you can basically directly apply onto this. Okay, let's move on. The valence shell electron pair repulsion theory. I like this theory. It's one of the most beautiful theories I've ever heard. Okay, and see, again, it's a theory, Drupad. It's not a concept. It's not a theorem. It's just a theory. It is something that 2 scientists, 2 crazy scientists, came up with for us to actually 3-dimensionally visualize this molecule. Okay, now Lewis' concept although explains the structure of several molecules, but in many cases it is found unable to explain the shape of the molecule because it is a two-dimensional figure. How can you have a three-dimensional structure and a two-dimensional figure? Obviously, you can't. In order to explain the shape of these molecules adequately, Sedgwick and Powell in 1940 proposed a theory based on the repulsive interactions of electron pairs in the valence band or valence shell of an electron. So they realized that electrons can exist as a lone pair, a lone electron which does not actually participate in any of the bondings, or it can exist as a bond pair. That is, it can exist inside a bond. It can exist outside a bond or it can exist inside a bond. For example, in the oxygen molecule, only two electrons of each and every oxygen atom is actually participating in the bond formation. The rest of the two electrons are stationary. They are doing nothing. Like it's basically staying there. Okay, now one thing that is common between both the lone pair and the bond pair is all of them are electrons. They are negatively charged. So every single time an electron comes in contact with the other, it repels it. So they came up with this theory. The name of the theory is what? Valence shell. That is the outermost shell. Electron pair. It can be valence electrons, it can be lone pair of electrons, or it can be bond pair electrons. But one thing that is common between both of them is that they repel each other. So valence shell, electron pair, repulsion theory. Okay, that is how this whole wording goes. Okay, now what did they do? What was so strange that they announced? Let's see. Now, postulates. What are the postulates that they have? The main postulate of this theory are as follows. The number of valence electrons present, bonded or non-bonded, present around the central atom decides the shape of the molecule. The shared electron pair are called the bond pair of electrons, and the unshared or the non-bonding electrons are called the lone pair of electrons. So you have two types of electrons in a molecule. Yeah. So, what's next? Electron pairs of valence shell repel one another because their electron cloud are negatively charged. We know that negative charge repels each other, right? Negative charge repels each other. So, basically, what is happening? There is some form of repulsion that is existing between the electron clouds. These electron pairs arrange themselves in such a way so that there is minimum repulsion and maximum distance between them. So, how does an at how does a molecule gain its shape? The molecule gains its shape because the electrons are consciously arranging they are consciously and constantly arranging themselves in such positions where the repulsion between the electrons will be the minimum. And how can you make the repulsion the minimum? By increasing the distance between the electrons. Okay, so basically what is happening? What is happening? The spatial arrangement is changing. Now I want you to imagine yourself in a lift with a few people. Okay, now when there are four people in a lift, let's assume that there is space in the lift for four people. Okay, like 5 6 people, but there are four people. Now, would all of you bundle up in one corner of the lift? No, right? You would all take the four corners of the lift. You would try to make maximum distance between each other so that you don't invade each other's personal space, right? That is a conscious thing that we do, right? We don't actually group together as a single bunch inside a lift. That would be so awkward and uncomfortable, right? So we try to give everyone actual space so that they can feel safe, so that they can feel that their personal boundaries are not being hindered. And that is what the electron is actually doing. See, physics somehow, I believe, gives these electrons the consciousness to actually perform their various tasks. Now, what is happening here? The valence electrons, the valence shell is considered as a sphere in which the electron pairs are localized on the spherical surface and a maximum distance from one another. So basically, you can consider this to be a sphere like this. This is the valence shell. Okay, on this valence shell, there are all these electrons on its surface, right? There are all these electrons on the surface. They have arranged themselves in such a way so that the distance between all the electrons is the maximum. Okay, next. Multiple bond is treated as if it's a single electron pair. Now, when we have double bonds, like for example, Drupad, look at this. You have a carbon, okay, another carbon, a carbon here, a carbon here, and I'm just drawing this. This is an incomplete structure. Okay, please don't blame me. It's just an incomplete structure. I just want to explain to you what it means. Now, this double bond here is considered to be a single bond when we are calculating the repulsion, because a double bond, once you know understand more about this, how a double bond is formed, it will blow your mind. When we do hybridization, you will actually see how a double bond is being formed. Okay, now this double bond is supposed to be considered as a single bond. Multiple bonds are supposed to be treated as a single electron pair. And what is happening next? And the two or three electron pairs of multiple bonds are treated as a single bond. So how many electrons are here? There are 1, 2, 3, and 4. 4 electrons are present in this double bond. So what are we going to do? We are going to consider them, all of them, to be part of a single bond. If a molecule has several resonating structures, the Vesper model is applicable to any of these structures. Okay, so you want to create a structure for a canonical form? Go ahead, it will be the same structure. Okay, next, a lone pair occupies more space than a bond pair since it lies closer to the central atom. So think of it like this. Okay, when there is sharing of electrons, when there is sharing of electrons between the two atoms, what do you observe? You observe that the electrons that are present in the surface are actually a little further apart. Okay, they are further apart from the surface, so they don't require that much space. But the lone pair of electrons are not being shared by any two atoms, so we can consider them to be closer. Okay, so they require more space. It's like basically, I know it's impolite to say this, but a healthy person, like a big person, will require more space on the seat, on a bench, compared to a thin person. Okay, let's move on. This means that the repulsion between different electron pairs are as follows. So you will have the maximum repulsion taking place between two lone pair of electrons, between a lone pair and a bond pair of electrons, and between two bond pair of electrons. Okay, so the lone pair repulsion is the maximum, then you have the lone pair bond pair, and then you have the bond pair. Okay, so what they're trying to say is, let's take the example of oxygen molecule. Okay, let's see. No, let's take the example of carbon dioxide. Oh, these are the bond pair electrons. These are the lone pair of electrons. Okay, understood? These are the bond pair electrons and these are the lone pair of electrons. Now, what they're trying to say is this repulsion, we are considering the double bond to be a single bond repulsion. Okay, be very careful. This repulsion, okay, and this repulsion is more than, sorry, this repulsion, this and this repulsion is more than, this repulsion is more than this repulsion. So this repulsion is called the lone pair repulsion. This is called the lone pair bond pair repulsion, and this is called the bond pair bond pair repulsion. So when you study all of this, you get to know that this is not the structure of what? This is not the structure of carbon dioxide. See, because the lone pair repulsion is the strongest, right? So carbon will try to align the oxygen like this. Oh wait, wait. Oxygen only has 6 electrons, right? What am I doing? I'm sorry, I made this mistake. So basically, this lone pair repulsion will be reduced to, because the lone pair repulsion is maximum. Okay, I think I should erase all of this. 1 second. Yeah, much better. Okay, so because there is lone pair repulsion here and here, the only structure that makes sense is that carbon should stay in the middle and these two oxygens should be as far apart as possible. And what is the maximum distance, that maximum angle that they can have? 180 degrees. Because at 180 degrees, these two lone pair repulsions will be the least. Did you understand this, Drupat? Yeah. So this is what the lone pair repulsion looks like. This is what the lone pair bond pair and the bond pair. So maximum repulsion can only happen in this structure. And in the next page, we will learn that this structure is called the linear structure. Okay, let's go. Next, the repulsive forces decreases sharply as the angle between the electron pairs increases. Right. Here the angle was less, right? But here the angle is maximum. So the lone pair repulsion has reduced to a large extent because the angle between these two bonds is 180 degrees, the maximum that you can have, right? This is the maximum that you can have, right? Let's move on. Next, they are strong at 90 degrees, weak at 120 degrees, and the weakest at 180 degrees. So if I were to draw the structure like this, carbon in the middle, a double bond here, and a double bond here, the repulsion would be maximum. Okay, no, sorry, not this one. Uh, this repulsion, this repulsion would be the maximum because the angle is 90 degrees. Okay, now at 120 degrees, the repulsion between these two would reduce to a very large extent because of the bond angle to be 120 degrees. Now, here the repulsion is the least because the bond angle is 180 degrees. I hope you understand this. I hope you have understood this concept clearly. Okay? Okay, let's move on. Now, thus, there is a great repulsion between lone pair of electrons as compared to lone pair and bond pair repulsion. The effect of these repulsions are the deviations from the ideal shape and are alterations in the bond angle in the molecule. Okay, let's actually go through this. Next, classifications of, no, wait. Oh, there was a neat and clean page. I had already taken print photocopy. I did not have the need to actually use this blurred image. I had actually taken a very good image. Anyways, I'll just go through this slowly like this so that you can see. Okay. So, what are the various shapes and geometry of molecules on the basis of Vesper theory? Okay. Now, we have categorized the shapes into two. One, where there are no pair electrons in the central atom, and number two, where there are lone pair of electrons. Next, so the geometry of molecules depends upon the total number of electrons, lone pairs plus bond pairs present around the central atom of a molecule. It is a convention to divide molecules into the following categories as geometry of molecules in which the central atom has no lone pair of electrons. If there are only two bond pairs and no lone pairs around the central atom, the only way to keep them as far apart as possible is to arrange them at 180 degrees to each other. The molecule is in such a case will be adapted known as a linear geometry. So this is what they're talking about here. See, there are only see look at the diagram of carbon dioxide. There are only lone pair of electrons. Sorry, there are only bond pair of electrons present in the central atom, and the central atom is carbon. Okay, now to make the repulsion the least, you will have to separate them by an angle of 180 degrees, and that is where you get a linear structure. I hope you understood the logic behind the linear structure. Okay, let's move on. Okay, now, so when you have an arrangement like this, you get a linear structure. This is what a linear structure looks like. But what if you want to make three bonds? Okay, and you don't have a lone pair. For example, BF3, boron trifluoride. Boron trifluoride has a valence electron. How many electrons are present in the valence shell of boron? Hydrogen, helium, lithium, beryllium, boron. The first two are present in the inner shell, rest of the three are present in the outer shell. So you will have boron, one electron here, one electron here, and one electron here. And fluorine, you will have electrons like this bonded here. Again, one more fluorine bonded here. Again, one more fluorine bonded here. So you can see that the repulsion between these electron pairs is reduced to a much larger extent for a molecule that can form three bonds. Okay, so that is why boron trifluoride looks like this. All the three fluorine atoms are in a single plane. All the three fluorine atoms are present in a single plane. So I can draw a plane structure like this. I can draw a triangle. This triangle indicates that all the three are in one single plane. Okay, and what happens when you have such a structure? You automatically get this angle, this angle, this angle to be equal. So if I consider this angle, this angle, this angle to be x, 3x is equal to 360 degrees. Therefore, x is equal to 120 degrees. That's how you get the bond angle of boron trifluoride to be 120 degrees. Because boron, which is the central atom in this case, does not have any lone pair of electrons. So the lone pair repulsion is actually not present. Okay, only the lone pair of fluorine is present, and it is arranging itself in the three corners in a single plane itself, so that the repulsions are reduced to a minimum. And to do this, it is basically making the angle between the two bonds to be 120 degrees. Understood the logic of trigonal planar structures? This is called a trigonal planar structure. Next comes the diamond structure, or what we call in chemistry a tetrahedral structure. Now, in class 10th, you had already studied that diamond has a structure that looks like this. Okay, every single carbon atom in diamond is attached by four other carbon atoms inside the diamond. So how does it take place? You cannot arrange all the four carbon atoms to be in a single plane because this structure does not exist. Okay, this is not going to exist. Why is it not going to exist? Because as we have discussed, the repulsion is maximum when the angle is 90 degrees. So you have to reduce the angle, sorry, you have to increase the angle from 90 degrees to some other angle so that the repulsion will remain as low as possible. So the Lewis structure for drawing this carbon is absolutely wrong. They don't exist in a single plane. This is how they look like. Okay, so basically three electrons, you can have three electrons in a single plane at a single time. For example, the four B atoms that is surrounding the A atom, you can have these four to be like this three B, this A, and this B is part of a single plane. Okay, so basically I want you to imagine a triangle like this. Okay, an actual triangle like this. Imagine a triangle like this. Okay, on in this triangle, imagine one corner of that triangle to be that of A, and the rest of the two corners are being shared by B. Okay, so it will look like this. The thumb is the A, and these two fingers that I'm holding is the B. So I'm getting a triangle like this. Now there is another triangle going up here. One B here, one B downwards. Okay, so you are having two triangles shaped like this, where the A is being part of both the triangles. Understood? So you can, if you want to imagine this, you can actually think of it as a tripod. Okay, the three B's at the bottom are being the three legs of the tripod, and the one B in the top is the place where you put your camera. Okay, so this is called the tetrahedral structure. Okay, tetrahedral structure. Understood this logic? Huh? Up or down? Okay, now a tetrahedral structure, every single bond angle, every single bond angle is going to be 120 degrees. Sorry, 109.5. I'm so sorry, it is 109.5 degrees. Okay, now what is so strange about this? See, the angle between A and B, ABA. So every single angle like this, B, A, B. This is the angle which is going to be 109.8 degrees. Okay, this is what they're talking about when they speak about bond angle. Okay, the angle formed by one B atom, one A atom, and one B atom in the molecular structure of the tetrahedral molecule. Okay, next you have the trigonal bipyramidal structure. That is, it is a structure where the central atom can form how many bonds? It can form five bonds. Now, when the central atom was able to form four bonds, we called it a tetrahedral structure. Three bonds, we called it a trigonal planar structure. Two bonds, we called it a linear structure. But here it is forming five bonds. Sorry, five bonds. Okay, that five bonds are arranged in such a way we call it the tetrahedral structure. Why? Because you can have, see, the central atom is A here. Okay, you're having a B here, a B here, and a B here. Okay, and it is forming a bond. These three, can you see the three B's here? This, and this, and this. They are all in the same plane as that of A. That is why, that is where the term trigonal comes. Okay, all of them, all the threes, all the three B's and this one A, all of them are in the same plane. Okay, next, there is one B at the top, one B at the bottom. Okay, so it literally looks like this: A, B, B, sorry, not like this. You have the B, the B, the B, A, the B, and the B. So these three will be in the same plane, and these two B's, one will be above the plane and one will be below the plane. Okay, this is how a tetrahedral structure, sorry, trigonal planar structure looks. Clear? Understood? Trigonal planar. Okay, now next comes six bonds. How do you share the six bonds? Similarly, instead of having a triangle in the plane in the middle, you have a square. Okay, like this. B here. Sorry, this is A. This is B. This is B. This is B. This is B, and this is B. So basically, you have how many sides will you have? You will have like this. See, one, two. This will be three, and this will be four. So basically, you will have, it's like this: four triangles at the top, one, two, three, four. Four triangles at the bottom. It will look like an eight-sided dice. Eight-sided dice. If you play Dungeons and Dragons or some other game which requires an octahedral dice, is eight-sided dice, you will have what? An octahedral structure. Okay, understood? This is how you arrange them. Now, every single bond, every single bond here in the plane will be 90 degrees. And this, the bond between B, A, I'll just highlight this, B, A, and B will also be 90 degrees. All the bonds are at 90 degrees to each other. You can imagine this. See, this, this 90 degrees, this again 90 degrees, this again 90 degrees. So every single bond angle in the octahedral structure is 90 degrees, whereas in the trigonal bipyramidal structure, at least the plane had 120 degrees. These all three angles were 120, 120 degrees and 120 degrees, and these two, only these angles were 90 degrees. You had three bond angles having 120 degrees and the rest was 90 degrees. Okay, but here in the octahedral structure, all of them are 100 and sorry, all of them are 90 degrees. I hope you understand this. Okay, in the next class, in your Wednesday's class, I would actually try to make these shapes using toothpick and clay, I hope. Okay, and I will try to show it to you. Okay, now, so what are the shapes that we have discussed till now? We have discussed the linear, we have discussed the trigonal planar, we have discussed the tetrahedral, then trigonal bipyramidal, and then octahedral. So what are some examples of linear? You have the BeCl2, the Hg2s. You have the CO2 is also an example of linear structure. Then you have BF3 and ALF3 in the trigonal planar structure. CH4, NH4 plus, and CCl4. Any molecule that forms four bonds and does not have a lone pair of electron, it will be what? A tetrahedral structure. Then you have PCl5 having the trigonal bipyramidal structure, and finally you will have your SF6, which will be an octahedral structure. I hope you understood till here. Any doubts till now? This is one of the most interesting topics that I like to teach. I really like teaching this chapter because when I learned this, it was one of the most mind blowing times of my life. Okay, so any doubts in this, Drupad? One second. So we have discussed all the shapes where you only have the bond pair of electrons. There are no lone pair of electrons present in the central atom. The central atom in each case was this one, the Be here, the B here, the C here, the P here, and the S here. Okay, all of these were the central atoms. no lone pair of electrons present in any of them. So these were the structures that we had. So next we will discuss the lone pair and bond pair of electrons together. Okay, and that we can do in the next class. I really hope you enjoyed my lecture today, and we will most probably finish this whole chapter by another 3 videos. In 3 videos, we will be able to finish it, and I hope you watch every single video and you also appreciate the same amount of appreciate this concept with the same amount of gusto as I am here doing, and I'll try to make all these concepts as easy as possible. Okay, if you